Way galaxy. This episode will be going extra galactic, so grab your mates, some snacks, and get comfy. So be sure to use the hashtag MQ Space Travels if you have any questions, and we'll be monitoring Twitter, Facebook, Instagram throughout the whole thing, and feel free to ask questions in the comments below on Facebook. So many of you might know our speaker, Dr. Devika Kamath, from episode 1. She's the creator of MQ Space Travels, and if you've missed episode 1, it's still available on our Facebook and will be linked in the comments below. Devika is a stellar astrophysicist and a senior lecturer in astronomy and astrophysics at Macquarie University, and she's internationally recognized for her exciting work on using dying stars to study the origin of chemical elements in our universe, and also to study the structure and evolution of single and binary stars. So Devika is going to take us on a space-hopping journey, but this time we'll be stepping outside our home galaxy, the Milky Way, and explore our amazing galactic neighbourhood. So come along and let's befriend our spectacular cosmic neighbours.
Thank you, Gabby, and hello, everyone. I'm very excited to take all of you and you, Gabby, on a trip outside of our Milky Way galaxy and kind of befriend, like you said, our cosmic neighbors. Now, this is a very special episode because, as some of you might know, or rather most of you might know, we in Sydney are in a bit of a lockdown. Ideally, we would have loved to do this in the observatory and being on site, but we've put this together for you despite the lockdown because I think all of us need space, and space is for everyone. So this time we're kind of doing this on Zoom, and we're hoping that because space has no boundaries, it's going to reach everyone and we're all going to have fun with it. So in this episode, we decided to leave our Milky Way galaxy, and what we're going to do is we're going to go outside and explore our neighborhood a little bit.
Great. Where's the first stop?
Well, so we've been getting a lot of questions about our poster, and in our poster is this amazing galaxy which is called M83. We sort of gave you a teaser on that object in the first episode. Now, M83 is sort of called as the Southern Pinwheel galaxy, and I think we should revisit M83 and take it from there.
Sounds great.
Fantastic. So there's another special thing about this episode, which is the weather gods have been really good to us, which means that we get to sort of go live, and instead of showing you stored images, we actually get to show you what we see out of our telescopes. So we've got Adam and Ben using two of our telescopes. One is the 9.25-inch telescope, and the other one is a 24-inch plane wave telescope. Now, the image on the poster was taken using our 9.25-inch telescope, but what we're going to do for this episode is we're going to kind of go between the two, and we're going to see if we can sort of have fun looking at the sky through our telescopic eyes. Now, a lot of the images from the last episode, for those of you who came along with us, were taken using the 9.25. So I thought this time we should start looking at it at M83 or the Southern Pinwheel Galaxy using the 24-inch. So let's get straight into it. And how we're going to do this is, for those of you who joined us last time, you might remember we used a tool called Stellarium. Now, it is my go-to tool when it comes to understanding the objects in the sky, or looking for them rather. So Stellarium is a free open source stellar map. It's a three-dimensional stellar map. You can have it on your laptop or your phone or your browser, and what it shows you is it basically shows you like a realistic image of what the sky is going to look like. So Gabby, have you used Stellarium before? I'm sure you have, but
I use it a lot during our observatory sessions here at Macquarie as well.
Absolutely. So what we're going to do here, and what Adam's done for us, is he's basically keyed in the position of M83, and it takes us straight to the constellation of Hydra and Centaurus, because that's where the galaxy sits in. Now, M83 sits approximately 15 million light years away from us, so that is pretty far away.
And Devika, can you remind us what is a light year?
Yeah, good question. So a light year essentially is a measure of distance, okay? So in cosmic scales, if you want to measure how far an object is or a galaxy is, especially when it's very far away, a good unit that we use in general is basically a light year. Now, to give you an idea, one light year is about 9.25 trillion kilometers. So for comparison, the diameter of our own home galaxy, the Milky Way galaxy, is about 100,000 light years. And just like you and I live in a suburb, we have these suburbs. Our galaxy has a suburb that's called the local group, and the local group spans of about 10 million light years across. So this particular galaxy, this one here, M83, I said that it's about 15 million light years away, which means that it's sort of sitting just outside of our local group. So we're actually visiting another cosmic suburb right now, if you will. We're going to now maybe look at this fantastic object, and we're going to source the image from the 24 plane wave telescope. Now, I'd like to talk to you a little bit about, how this process works. Now, what you see on your screen, hopefully, is essentially what we call a GUI, or a platform, which is relaying to you, Gabby, and all our viewers what is being captured at the telescope. So the telescope is connected to the computers using wiring and network. And essentially, this is the kind of image we're going to be looking at if you're in the magic control room, as we called it. So what you have here is when you are looking at an object, and Adam has already done this for us for the first object, there's a few steps that, go into play before you actually see an object on the screen. Like for now, you see this amazing, beautiful object, which is M83. But in order to get this, you first, of course, have to point the telescope to the object. You have to make sure that because the sky is moving, the telescope is auto-tracking and also auto-focusing, because if your object is not focused, then you're going to lose a lot of clarity for the object. Now, something else to remember is that you can see this GUI over here, and it has a few panels. And what these panels essentially give us is it gives us information on things like exposure times, how much of signal is being recorded from the image. And at the bottom, you have a histogram, or something that allows us to change the scale of what the image looks like. So you can change the colors of the image to make it look as appealing or as intricate to be able to study the different features. Now, for those of you who missed episode 1, I'll say go and have a look at episode 1 to understand what the colors are when you actually have an astrophysical image. But we'll also talk a lot about colors in this episode as well. Now, one thing I'd like to say about this image is we've been looking at this particular M83 image now, and you can see Adam's playing a bit with the colors that you get from the camera that's connected onto the telescope. It's been exposed for about 30 minutes, so it's about half an hour of an exposure, and normally these are taken as smaller exposures. So your exposures can go anywhere between 30 seconds or a minute, and then you stack all of them up, and the more you stack, the more amazing your image is essentially going to look like. Now remember, this is done using the 24-inch telescope. And something I'd like to say about the 24-inch telescope is at Macquarie University, we're very proud about it because it is one of our research-grade telescopes. Now, this is a telescope initiative led by one of our colleagues, Dr. Christian Schwab. Now, they have also they have built a spectrograph, and we are using this to do state-of-the-art research on exoplanets and variable stars. But for today, we're not using the spectrograph because we're interested in pretty pictures. So Adam has connected a color camera to the telescope, and he's kind of sourcing us the images. So let's look at the image itself, because I think a lot of astronomy is looking up at the skies and enjoying and, just kind of soaking in all these amazing features. M83 is one of the brightest barred spirals in the sky. And Gabby, do you see the bar that's extending out of the galaxy there?
Yes, I think I can see it, and I can see some big, really spread out spiral arms in there.
Absolutely. So this galaxy is big enough and bright enough to be able to be, looked at using a small telescope like the one we have, small but powerful, but also a pair of binoculars. And in fact, it's quite amazing how alike it looks to the Milky Way. Like if you've seen many images of the Milky Way, it looks very similar to this, isn't it?
Yeah, it sure does.
Yeah, but remember the M83, the one we're looking at now, the southern pinwheel, it's only half as big as our Milky Way galaxy. So we're looking at about 50,000 light years across. And what I like about this particular galaxy is it's so proud of the way it looks. It's showing itself in all its glory, and we're looking at it face on, and what you can actually see, as you pointed out, Gabby, you can see these beautiful spiral arms extending from this bar-like feature that you see in this image from the 24-inch. Now, you can kind of observe, if you squint your eye a little bit, these dark dust lanes. Now, this is essentially where, the dust is residing, and there's many, or rather millions or hundreds of star-forming regions that are also sitting in these dust lanes. Now, remember, star-forming regions are what we call as stellar nurseries, and this is where all the stellar births happen, and that's essentially where you would go if you're looking for newborn stars. Now, in this image, despite being from a small telescope, you can still see the fact that there's blue stars. So is that something that pops to your eye?
It really depends on the color scheme there, but where if Adam puts up the blue,
yeah, so if you
can
zoom
sort
in
of see them in there.
That's right. So if you zoom in there, you can sort of see kind of brighter spots in the image compared to the more redder hues. I mean, again, yeah, so the blue colors are going to be relative to how red the image is because of the color camera that we are using. But what we see for these blue stars are they're essentially hot stars. So they're young, they're hot, they're massive. They don't live long, but then they are essentially massive hot stars, have a more bluer shade rather than the cooler ones, which tend to be more towards the redder and orange colors. Now, one thing you will notice as Adam has zoomed into this image of M83 is this central glow. It's quite spectacular, isn't it? You see the center of this galaxy glow, and this is essentially what we call the nucleus of a galaxy. Now, Gabby, let me ask you, what do you think sits in the very center of a galaxy?
Well, seeing as I do astronomy, I'm sort of cheating here, but I believe it'll be a supermassive black hole of some sort.
That's right. So it is a supermassive black hole, and I'm glad you answered that question. Thank you very much. I'm proud of you. So, so essentially, but we all know that supermassive black holes are you can't really image what's in the center of the black hole because of its extreme gravitational potential and the extreme gravity that it has. But the light that you are seeing essentially comes from millions of smaller stars, older stars rather. Now, these stars are very old, and in most spiral or barred spiral galaxies, they tend to sit around the central nucleus, and that's the glow that you're seeing. So it's not the glow from the supermassive black hole, but it's actually the glow from the center itself. Now, one thing to kind of mention about M83 is the fact that it's had a lot of supernova remnants go off in the past. We're talking about hundreds, 100 massive stars have exploded in the past. And if you're someone who's interested in remnants, then that's the place you go to because you can study a lot of stars that have already died. The claim to fame for M83 is the fact that it's had about 6 supernovae go off in the last 100 years. So it started around 1923, and the last one was just a little before I was born in about so it started in 1923, and the last one exploded just a little before I was born, which is about 1983. So that's quite interesting, and I find that really quite fascinating because one way to get supernova activity in stars, in galaxies, is also when you have two galaxies merge. And remember, nothing's staying constant in space. Everything's moving relative to each other. So there's always the possibility when you have interactions between two galaxies. And when that happens, there's a possibility where gas clouds can collapse because it gets attracted to denser regions in the merger process. And then you can sort of have new massive stars that are born that quickly die as exploding supernovae. So there's a lot happening in M83 despite its small size compared to our Milky Way galaxy.
So just to rehash what supernovas actually are, is they're the exploding remnants of dying stars?
Yes, any star that is 8 times the mass of our sun. So stars that are within 1 to 8 times of the mass of our sun, they die more elegantly. They kind of just take off the outer layers. But a star that is, greater than 8 times the mass of our sun, they have these fatal explosive deaths that we call supernovae.
And can we see? So we've got a really nice image here from our telescopes, but obviously some bigger telescopes might have taken a picture of this galaxy. Can we see one of those?
Yeah, let's do that. So let's have a look for comparison at an image that's taken from Hubble's wide field camera. And I think one thing you will see here is that the image opens up and you can see the dust lanes I was talking about. You can also see the pink hydrogen gas, which is the star forming regions, and hopefully you can see even more clearly the blue stars that kind of pepper the galaxy, which are these massive stars. Now, Gabby, I have a question for you. So if you have to compare, and because you're familiar with galaxies, if you have to compare M83 spiral arms with our galaxy's spiral arms, what would you say is the main difference?
Well, I guess the Milky Way, I feel like we have more spiral arms than the this galaxy M83, and are they a bit more compact, right? Than Milky Way's bigger, but I feel like there's more of them.
Well, I think we should tell our viewers that there is no actual image of the Milky Way galaxy. I think it's very important to remember that think of yourself as a pepperoni in a pizza. I mean, there's no way that you're going to have an image of the pizza because you're in it. So only what we know of our Milky Way galaxy is, imagine you're that pepperoni or an olive if you're vegan, and you're looking at the pizza, you kind of see one part of the galaxy. So based on that, and using smart galactic models, you are able to come up with what the galaxy might look like. So every image of the galaxy, our own galaxy that you see, guys, is a sort of a representation of what we think our Milky Way would look like, because we can study a lot of the parameters of the Milky Way very precisely. Now, in this case, of course, we are outside of our galaxy. I mean, this is outside of our galaxy, so it's a little bit easier to image. And you're right. So the observation here, and I hope that you and our viewers are able to appreciate it more with the high resolution image, is that the spiral arms are much more extended, and they're almost kind of going outwards and a little bit detached almost from the galaxy. In order to understand why that happens, it's kind of important to see what is the shape or what are the different components of a spiral galaxy. Now, remember, we said M83 is a barred spiral galaxy, and that's because it has a nucleus, of course, as we talked about, and then it has this configuration of stars that kind of arrange itself like a disk. Or like a bar. So basically you have this bar, and then you have the spiral arms that are emerging from the bar. These kind of galaxies that have very open spiral arms, they're actually called grand spiral design. So they're called slightly differently because they are indeed different to a normal spiral galaxy that it has a little bit closer kind of arms. And if you look at, the percentage of galaxies that have grand spiral arms versus more tighter arms, the majority of them have tighter arms. So there's only about 20 to 30% of them that have these more opened up structures in the arms.
Oh, that was very interesting, Devika. So in the interest of time, let's move on. So we've seen two different types of telescopes here. Can we have a look at one of our telescopes at the observatory in any detail?
Yeah, sure. So maybe what we can do this time is last time we had like a view of our entire observatory. So this time Adam's prepared for us a virtual tour to one of the telescopes, which is a 24-inch, which is what we just used. So maybe we can have a look at that.
Sounds great.
Let's do it.
The Planewave CDK 600 has a 24-inch primary mirror with a focal length of 3,974mm at focal ratio of f6.5. The telescope was installed in late 2019, and due to the size of the mirror, a crane was needed to pass the mount and telescope tube through the slit of the dome. The telescope uses a corrected Dowell-Kirkham design, which includes a primary and a secondary mirror, and several lenses produce a large 70mm image circle. First light for the telescope was on the 11th of January this year, with an image of Hubble's Variable Nebula.
You have a primary mirror.
The Planewave
and essentially that's the configuration. So it's on an alt azimuth mount, which means it can move in this sort of a direction. And one of the objects that was flashed in that video at the very end was one of the very first objects that we observed, and it was a nebula. So I think that's sort of pretty cool. So we're hoping that, you know, when things go back to normal and the lockdown's extended, we can actually have behind the scenes for one of our episodes where we're going to take the viewers on what it is to actually be at the observatory observing through our spectacular telescopes.
Well, that sounds like an exciting time. So I've got some questions from the audience here. Okay. So Louise is asking, if we're seeing a galaxy live, would we be able to see it move?
Wow, so that's a really, really good question. Well, technically, it's difficult for various reasons. So when we talk about galaxy movement, there's a few ways in which galaxies move. Well, not a few ways, there's a few reasons rather. Now, first thing to remember is galaxies can be coming towards us inside a small bubble, and we'll talk about this. But also, one thing to keep in mind is the universe is expanding. So we know that every galaxy relative to another galaxy is kind of receding from each other. So there's a few movements to take into account. And of course, galaxies are also rotating. They're spinning, especially the ones with the spiral arms. They have a lot of spin that's going on. So when we think about movement, they can be moving towards us, and then there's the expansion of the universe, and there's the spin. Now, when it comes to actually watching a galaxy move in human lifetime, it's almost impossible to do that. But astronomers have a way of understanding whether galaxies are moving towards us or away from us. And we do this using light and colors. So when the galaxy is moving towards us, for example, the light is shifted towards bluer wavelengths, and this is the concept of Doppler shift. And then we kind of can tell that, for example, if you observe a hydrogen line, ideally the hydrogen line has one energy and it should peak at one particular frequency or color. Okay, but when this galaxy is moving towards us and you observe the same atom of hydrogen, you'll see that the peak or the color of the hydrogen atom is actually shifted because it's moving towards us. Now, the same thing for something moving away from us, or generally the expansion of the universe, we call that concept redshift. So you can kind of understand galactic movement by measuring the velocity of galaxies, but to see it in real time is going to be difficult. But of course, you know, we do have theoretical models that simulate, for example, the collision of galaxies and so on. And I think at some point we might get a chance to talk about Andromeda, our nearest galaxy, merging into our Milky Way. So maybe at that time we can sort of revisit this. But yeah, it's a really good question.
Yeah, and we've got another question from Robbie, which we sort of talked about in episode 1, but are the colors of space shown in these pictures real colors?
Yeah, so that's, of course, a very, very interesting question again. And I think this is sort of what we talked a lot about in episode 1. So the answer to that is, well, they're sort of chromatically aligned colors. So we decide to choose various frequencies that come out of a particular object, we give them colors. And therefore, I would say that these are near true images. But if you had to walk through space with your bare eye, you're probably not going to see the galaxies the way they appear in a color camera or in the Hubble's camera, because what happens with these cameras is you have different bands, and each band collects light in one particular color or frequency, and then we superimpose them together, and then we get these colors. I think it's something we talked about last episode also, which was what is the color of the universe if you have to average everything out? And the color is sort of like a beige, because that's the average light that you get from all the stars and galaxies. When you average all the colors, if you have to go through space with your eye, you're kind of going to see that sort of a color. And it's also because our eyes, the human eye, is more sensitive to these colors rather than purple or green or other colors. But yeah, please have a look at episode 1. We've talked a lot about the concept of colored images in astronomy and astrophysics.
Definitely. So now that we've answered some questions, I can't wait to space hop to the next object. So which one's that going to be?
Okay, so for the next object, where I decided to take you guys is Centaurus A. Now, Centaurus A is rather close to M83. So when it comes to, visiting the next neighbor, I think it's the best one in line. So we'll take up Stellarium again, because we're going to go hunting for Centaurus in this case. So Centaurus sits in the complex group of galaxies in the constellation of Hydra, Centaurus, and Virgo. So once you key it in, you can sort of see these configurations in Stellarium. So the Centaurus A subgroup of galaxies are around 11 to 15 million light years away. So kind of similar distance to M83. So they're kind of all neighboring subgroups of galaxies. If you had to walk, you're essentially walking from one suburb to another. So not very, very far away. Remember, we're still inside what we call as our own supercluster. Now, when you think of the configuration of the universe, you think of it as this massive web-like structure where you have galaxies clumping up together, and then you have voids, which is essentially dark matter and dark energy. But of course, this is still unknown. These are all very current questions that astrophysicists are trying to understand. But our Virgo supercluster essentially houses around our local group and also other local groups like the M83 local group, as well as the Centaurus A local group. Okay, so here's Cen A in the Stellarium app. Now, an interesting thing about Cen A is the fact that it was discovered in the 1800s by this Scottish astronomer called James Dunlop, and he did this from Parramatta in Sydney. So I live not so far away from Parramatta. I'm normally always very proud of the fact that, well, there were galaxies discovered in my, local council. But I'm not so excited about being close to Parramatta today, because, of course, as you know, for those of us in Sydney, we've got a stricter restriction. But I think there's an incentive to kind of stay motivated. If James could go and discover galaxies, I guess there's a lot we can do, even though we're sitting at home.
Oh, Devika, you win some, you lose some. You discover galaxies, you got to be in lockdown.
Right. So maybe this is a perfect opportunity for all of us to go and discover some galaxies. So for those of you living in Parramatta, here's a big shout out. A lot of galaxies were discovered in this very own suburb. Okay. But anyway, let's take the on-sky image and let's see what it looks like through a telescope. So I think this time what we'll do, depending on which telescope we have set up, so this one here is the 9.25-inch telescope, and we're looking at Centaurus A. Now, once again, this is the live sky view, and I love how the GUIs give us a lot of information, once again, on what the observations are, what the exposure times are, and so on. Now, one thing to remember is The GUIs for both the telescopes are, of course, very similar because at the end of the day, the physics that powers the telescope and the parameters like exposure time, gain, the histogram that displays the image, all of that stuff is essentially the same. So yeah, so Sen-A is once again quite bright. It's like the fifth brightest in the sky. So this is an amazing amateur astronomy target. If you have a small but powerful telescope or even a powerful binocular, you can actually observe a Sen-A, especially in the southern hemisphere. So this is one of my favorite galaxies, but I say that about every object. So I think I'm very, very biased.
And Devika, this image looks a little bit familiar if you've been following our Facebook pages.
It has. So here's a question, and please, guys, add this in the comment box. So one of our posts was about, we blurred an image and asked you to identify which one it was. So it is Sen-A. Ta-da! So you got that right. Then you should be very proud of yourselves, and you are an amazing amateur astronomer or astronomer in the making. So well done. You know, the thing about Sen-A is it's very different from M83. And Gabby, you know, what do you see as obvious differences? I see quite a few as well, but I'm keen to hear what you think.
Well, it's not face on to us is my first observation.
Very good. So let's take a moment and explain what face on is for our viewers. So when you look at an astrophysical object, of course, the characteristics of the object are important, and this comes from the object itself. Like, for example, it has a nucleus, it has a bar, it has a spiral arm. But remember when we spoke about M83, I said, you know, it's really proud of its beauty and it's kind of showing itself in its face on glory. What that means is M83 was showing itself to us like this. Now, if I have to tilt my hand like that, I may have spiral arms, but you can't really tell how many, or you can't really tell if I actually have any. And this kind of a view is normally called an edge-on view. So what Sen-A is doing here is it's kind of edge-on, you know, so it's a little bit, makes it trickier in understanding of what the shape of the galaxy actually is. And there is a little bit of debate when it comes to the shape of this galaxy. But I think, you know, some of the models that we have for galactic evolution and structure tell us that this is likely to be an elliptical galaxy because you really can't see this spiral arms here. And then, of course, it has this big dust, kind of a dust lane or a dust enshrouded by dust. So I think this is nice to appreciate and understand that, you know, galaxies have different shapes. We've seen barred spirals, and this one here, once again, like I said, we don't know for a fact, but we think based on our observations and our theory that this is likely to be an elliptical galaxy. Now, the interesting thing about this is one of the reasons why it looks a little bit complicated when it comes to its shape is because there is a theory that is you know, based on models again, where we think that Centaurus A is a large elliptical galaxy that might have in the past collided with a smaller spiral galaxy. And when this happens, what essentially the output of it is a little bit unknown. So very often, the majority of galaxies, if you look at in terms of shapes, are spirals. And the idea is that when two spirals merge or collide, they form an elliptical. But what happens when an elliptical interacts or merges with a spiral is a little bit unknown. And we think that that's sort of what might be happening with Sen-A. So it's likely to have been an elliptical galaxy that has undergone, once again, like M83, this has also undergone a collision or an interaction with another galaxy. Yeah, so let's zoom into this on-sky image taken using our 9.25-inch telescope. And I think we can start seeing sort of investigating certain features that stand out. Now, the bulge of this particular galaxy, Sen-A, is mainly composed of older red stars, and that's kind of what you can tell, despite also this being a color camera, but still you can sort of tell that majority of the stars here are mostly older red stars. And of course, there's this massive dusty disk that sits here. We think, or rather we know, that the center of this galaxy also contains a supermassive black hole. Now, ideally, supermassive black holes can get anywhere from 1 million solar masses to, say, 100 million solar masses. And this one is estimated to be around 50 to 55 million solar masses. Now, there's reasons why we know that Sen-A has a supermassive black hole. And Gabby, would you like to kind of brainstorm on why this might be the case?
Well, there's a lot of light coming from the center, would be one of my first guesses.
Well, ideally, what happens when you have a supermassive black hole in the center is there's a chance where, you can sort of get emissions because of matter that is being twirled into the supermassive black hole, right? But of course, sometimes it's hard to observe that in the optical, like this particular image with the 9.25, and definitely not with a small telescope. So you do need to call in X-rays or more high energy, like radio waves, in order to be able to study these emissions that come out. So we'll get there in a minute, but I think the other things to also appreciate are the dust lanes that you kind of can see. So this is a very, very dusty galaxy that has a lot of old stars, and I find that really, really quite spectacular. And you can you can tell why we kind of wonder if it's actually a spiral galaxy, because it's very hard to notice or detect the spiral features in this particular galaxy. Let's have a look at a high resolution image that we've put together for this particular object. And this image is actually what we call as a composite image. Now, what we have here is the top panel, which is a composition of 3 different frequencies. The blue shows the X-ray, and this is the small panel at the bottom. The pink and green ones at the left to my right are the same image that is Sen-A, but in radio frequencies. And the orange and yellow show Sen-A in optical. So Gabby, I guess when you look at the optical one, you can kind of relate to the one we saw from our 9.25, because our 9.25 also works in the optical.
Yeah, it's interesting that they have different shapes in the different frequencies as well.
Absolutely. And the reason for that is because different components or astrophysical objects peak in different frequencies. For example, if you look at the X-rays, what you're detecting in X-rays is essentially a lot of the hot gas. That kind of stuff is not normally peaking in the optical. So if you want to study, for example, dark matter, a lot about dark matter, what we know, and we still don't know a lot about it, but what little we know about it is all studied in the X-rays, for example. So if you look at this image with the blue panel at the bottom, what you're studying there is essentially a lot of the hot gas and possibly some amount of dark matter being detected in X-rays. And then, of course, you have the optical. Now, the glow from the optical that you mentioned, Gabby, it's most likely because there's a lot of stars, like I said, but there's a lot of dust. And when starlight is absorbed by dust, it's also re-emitted. So you get this amazing glow, and that's kind of the glow that you're seeing. So it's basically a combination of starlight and how reflection works from dust grains. And then, of course, you have the radio frequencies that show these lobes, or I would call them jets. They kind of are emitting from the center. So you can't really see the central parts of the galaxy, but you can kind of see these beautiful lobes. And these are what we call as radio jets, and they peak in radio frequencies. And this is essentially pointing or giving us direct evidence of the presence of the supermassive black hole. because what essentially happens when you have a supermassive black hole is you have material that is being dragged into the supermassive black hole. Now, when this happens, you have high energy rays that are emitted because of this so-called accretion process. And these high energy waves are what we see as beautiful radio jets. So I think I'd like to take a moment here to say that it's also really important to study an object in different frequencies, because if we only had the optical, we would not have been able to say that there's a supermassive black hole in the center. And if we only had the X-rays, you wouldn't have really been able to study the features of the galaxy, like the stars and, you know, the shape and so on. So the image on top is basically a composition of all these three images. Now, I'd like to say once again that these colors are chosen to match the frequencies, or, you know, whichever part of the electromagnetic spectrum, which is light, that you look on. So it's not the true color, but it's essentially colors that are allocated to different frequencies of light. And when you put them together, you see this amazing, spectacular display of Cene, and we call this galaxy a radio galaxy. Now, many other galaxies have, you know, supermassive black holes in them, but I think to remember is that not all galaxies are radioactive, or rather active galactic nuclei. So sometimes you can have a supermassive black hole that is quite quiescent, or think of it as being asleep. It's not yet hungry. So it's only when there's a lot of accretion of matter into the supermassive black hole do you actually get these jets out. So that's kind of what differentiates a normal galaxy from an active galaxy.
Okay. Thanks, Devika. That's really interesting. I'd like to also point out the in the radio, you can't see the dust in the image.
Yeah, that's right. Because dust has the capacity, or basically peaks in infrared, or a little bit, you know, in the optical. So for example, when you looked at, you know, the past galaxies, you saw these dark dust lanes. And the reason it was dark is because dust absorbs optical photons. So when light is coming in the optical wavelengths that our eyes can see through, dust basically absorbs them and doesn't let them pass through. So the only way you can study or probe dust is if you look at the infrared. So that's kind of one of the reasons why, you know, many of the telescopes are studying the dusty parts, or the star-forming regions, which is full of dust in space, through infrared frequencies. Now, the reason, like I said, you have the yellow kind of glow is because light can be scattered by dust in sometimes, and that's kind of why you have that. So yeah, it's quite layered and complicated, but once you understand which sort of object emits in which frequency, you can sort of start, you know, associating colors that you see in these beautiful images to the various astrophysical components of an object.
Yeah, it's really interesting. So we've got a question here from Patrick, and he's asking, does a galaxy form first, or does the black hole at its center form first?
Yeah, so that's a very, very interesting question. And I think the answer to that is there's sort of two theories on, well, first let's talk about how a galaxy forms, right? Now, there's two ways in which is being proposed there's one preferred way, of course, but let me present the two ways. One is you have this massive dust cloud, and this breaks up into smaller clouds, forming stars that all combine together, and then you have a galaxy. The other way you can form a galaxy is you have basically dust clouds that are, you know, of a smaller size, and these collapse within themselves, and then they form stars, and then you have a mixture of dust and gas, and then many small dust clouds clump together, and then you get this big galaxy. Now, ideally, we as astronomers, based on the information we have from our observations and from our theoretical models, we think that it's essentially the smaller clumps combining together to form one big galaxy. Now, the concept of where does the supermassive black hole come from, we think that this is being formed during the formative process of the galaxy. So you have these dense regions of gas and dust. Now, a lot of this, I'm talking about, millions of solar masses can collapse into forming these massive, supermassive black holes. So it's a little bit different from a stellar black hole, where you have a massive star that can go off as a supernovae, and then the core of the star collapses into a stellar black hole. But in the case of a galactic black hole, it's a supermassive black hole, and that is essentially formed during the formative process of the galaxy itself. Very good question.
Yeah, too.
But these are state-of-the-art questions that we astronomers are still working on and trying to understand. So it's great that we're able to with more advancements in telescopes, we're able to probe deeper and older parts of the universe, and then we piece together the puzzles.
Yeah, it's interesting to see that even you have been in this field for a long time, and you still don't have all the answers. We're still asking questions, and there's heaps of questions out there in the universe for us to answer. Which is good for me, because that means I'll have a job eventually.
Gabby, you are a spectacular student, so you have nothing to worry about. But I must say that, when Gabby introduced me, she did say that I'm a stellar astrophysicist, and that essentially kind of speaks for the kind of research I do. I work a lot on using stars as probes or tracers to understand how the chemical elements in the universe are formed, how when you have stars, how do they evolve? Now, what we do is the information that we have, we give this to our colleagues who work with galaxies. And they run then galactic models to understand how galaxies are formed or how galaxies merge. So we're all kind of codependent, or, we all work together because our models feed the galactic models then feed the cosmological models of the universe. So it's quite a collaborative field, astronomy and astrophysics, and that's something I love about it, because you learn a little bit of everything, and space is for everyone. So I think that's one of the reasons I love doing astronomy. So yeah,
it's definitely a really interesting field to get into. So we're just talking about a composite image of different wavelengths and different frequencies and different colors, but we had on our Facebook and in our background images an image from the Hubble Space Telescope, which is called a deep field. This isn't a composite image though, but it has a lot of different colors in it. So where are these colors coming from?
Yeah, good question. So this image that is showing on our screens, and also where we're floating around, is basically called the Hubble Ultra Deep Field. Now, this is taken using the full range of colors available to Hubble through its camera, which is called the Wide Field Camera 3. Now, Hubble's full range of colors in the Wide Field Camera extends from ultraviolet to optical to infrared. So these are the different frequencies it's getting. And once it's looking at one particular patch of the sky, it's kind of accumulating or collecting all the exposures. And so basically those are the frequencies you're looking at, okay? Just keep that in mind. Now, coming to the colors itself, what we're looking at is essentially the true colors in the ultraviolet, optical, and infrared of these galaxies, which means we're able to probe stellar content, so stars, and we're able to study a little bit the dust and some hot energy, because you can also study these stars in the ultraviolet. Now, the reddish colors that you see is because this is coming from older galaxies that have older stars, and this is normally showing up in a more redder color. And if you look at these bluer galaxies, and some of them, if you look keenly, you'll also be able to see the spiral arms in them. These are more younger galaxies. I'm talking about galaxies that were formed, say, pretty much as old as young as maybe 1 million years ago or so on. So these are galaxies that have a lot of young stars. They're massive, they're bright, they're bluer. So you can kind of tell the average color. If you have to pick two colors, you'd say orange and blue. So I want you to think of, the orange one as most likely ellipticals, older galaxies representing galaxies that were formed, just when the first galaxies were formed. Now, we're looking at about 100 to, well, actually 10,000 galaxies in this image. And the smallest, reddest ones, maybe 100 of them, are amongst those galaxies that were formed when the universe was only 800 million years old. So, the universe is born at a time t = 0, and its age increases. Currently, we know the age of the universe to be about 13.7 billion years old. And these orange galaxies were formed right at the start. Whilst these ones, the blue ones that I'm looking at, and I think you can kind of notice them yourselves, they were formed when the cosmos was about 13 billion years. Now, it took a lot to make this image. If you point your phone or a telescope, even if it's a very big telescope, if you point it in the sky, you're probably not going to land up with this image. There's a bit of a history behind this image. So this image was made over about 800 exposures. So the Hubble telescope did about 400 or 450 orbits around the Earth, and the total exposure time from this entire, setting was about 11 days or so. So, and the patch of sky we're looking at is kind of the size of the nail of your thumb. Well, it depends on how big your nail is, but on the average, if you hold your thumb up and you look at the small nail that you have there, that's the patch it's looking at. And we're looking at about 10,000 galaxies in that tiny patch of sky. So when you go outside and you look at the beautiful night sky, you see a lot of stars, but remember there's millions of galaxies that are expanding, or rather, in the expanse of the observable universe.
Yeah, this image blew my mind when I first saw it, because I thought it was just an image of stars, and then someone explained to me what happens when we image stars like this, and you can sort of see some of these specks of light, they have sort of a cross in them, and that's a star. But everything else is a galaxy.
Yeah, absolutely. And that's right, Gabby. So essentially, I would say there's less than a handful of stars in this image. There's only the ones that have this little aberration around it is essentially a star, and everything else in that small patch that you hold up of your thumb is essentially 10,000 galaxies out there. And that's kind of gives you why we say, it gives you a feeling for why we describe the universe as infinite. Because, if you think about the size of our observable universe, and I call it observable universe because that's the extent of our universe we know today. And the staggering number is around 90 billion light years across. Okay, remember guys, a light year is 9.25 trillion kilometers. So that's the massive extent of our observable universe. Now, when, if you're students in school, when you start doing your research in astronomy and astrophysics, you never know, you might have the technology that is going to help us expand this size of the observable universe and probe even deeper. And in that, I want you to think of just your little thumb and think of these numerous amount of galaxies that sit in it. It's pretty spectacular.
Yeah, it is pretty spectacular. So, Devika,
yeah,
where are we off to next in our adventure then?
Okay, so let's make another stop, not so far from Sen A. So we're sort of, in the neighborhood still. And this one is called the Tweezers Galaxy. Now, it's a very interesting one. And what I'm going to do this time is we'll start off with the Stellarium, as usual. Now, Tweezers Galaxy, like I said, we're not so far from Sen A, so it still sits inside Centaurus. And of course, it was also discovered in Parameta. So, guys, all of you there, so if you kind of are in Parameta, we've got big shoes to fill. But for now, let's stay at home. But anyway, so what we're going to do is, that's the Tweezers Galaxy, and you can see it's quite a small little thing, but we're going to have a little bit of fun with it, and we're going to get Adam and also BJ And some of you might remember VJ from last episode, who's also helping us with one of our telescopes there. So what we're going to do is we're going to focus both the 9.25 and the 24-inch on the Tweezers Galaxy to give you a live comparison of the images you can get from these two telescopes in the observatory. Now remember, the Macquarie Observatory has a lot of telescopes. Like in the last episode, we used a 16-inch, for example. And Gabby, if I'm not mistaken, you're wearing one of our open night t-shirts, and that image was taken using one of the Macquarie telescopes. Is that right?
I definitely am, and this is the Orion Nebula for Astronomy Open Night 2019, taken by Adam Joyce. And he's going to kill me for not remembering which telescope it was taken with. I think it was the 16, but he'll correct me later if I'm wrong. Oh, the tech. Oh, it's the tech. It was the tech. It's all good.
I was just going to say, yeah, it was a tech, and it's one of my favorite. I mean, Orion is it's everybody's favorite constellation, and the Orion Nebula is just amazing. So yeah, there's a lot of spectacular things you can do with small telescopes, including wonderful T-shirts like the one Gabby's wearing. So anyway, so we've got the setup going here. So I'd like all of you to kind of appreciate the images that we get out of the 9.25-inch, which is on my top right, and the 24-inch telescope, which is on my bottom left. Now you'll see that the orientations of these telescopes, or rather the objects, are a little bit different. But no matter, it's the same object. It's just how you look or point the telescope in the sky. The 24-inch has a different sort of an orientation because it's an alt azimuth mount. So it just looks at the object slightly differently. Now you'll see that the GUI is very similar in both the telescopes, like I said. And I'm going to let you decide which one you like, and please enter your comments in the enter your likes in the comment section below. But Gabby, I have a question for you and also for our viewers. And my question is, what do you think the shape of the Tweezers Galaxy is? Okay. So we're going to keep looking at the two on-sky images, and we're going to get more and more exposures, maybe that kind of reveals some features. But yeah, it's an interesting question because once again, like Sene, this is an edge-on galaxy, but it has certain subtle hints that give away the shape of the galaxy. So look at it, think about what we've talked about, and maybe Gabby, you can tell us if any of our viewers have some opinions, and what do you think? What do you think the shape of this galaxy is?
Well, before I sway the viewers with my choice, because I actually know what type of galaxy this is, when I was looking at it for the first time, I said, you know what, it looks a little bit elliptical because you can't really tell all that much. It's a bit of a blur, a bit of a smudge on the sky.
Right, yes.
A little bit elliptical in shape. But, and this might be a hint, I know better now. So
let's think about the hints, right? So some of the hints to keep in mind is that first thing is that the size of, I mean, it doesn't really matter when it comes to the shape of the galaxy, but just to let you know, the size of the Tweezers Galaxy is very similar to our own Milky Way. In fact, that's one of the first galaxies we've seen today in our live stream that has a size that's very similar to our Milky Way. Now, you can sort of tell more so from the 24-inch, or maybe even from the 9.25, actually, you can kind of see star-forming regions that are these dusty pink-colored clumps together. And you know, like I said before, when you see this kind of regions, they're essentially where stars are being born. Now, you might remember, and this is another clue, that when you have young galaxies, then you've got a lot of star-forming stuff going on, and then the older galaxies that were formed initially when the universe started, they're much older, and they don't have so much of star-forming galaxies going on. They're more redder. But these ones they tend to be a little bit more bluer because of the star forming. So anyway, but that once again depends upon the color cameras you use in your telescope. But let's give the viewers some time to think about what the shape of the galaxy is. But in the meantime, I think one of the points I'd like to bring forward for this particular galaxy, the Tweezers Galaxy, is that you can't see it using optical telescopes, but X-ray and infrared observations of the Tweezers Galaxy has revealed a significant amount of emission in these two frequencies, which means that the nucleus that sits in the center, just like Sen-A, is quite active. So you're looking at a rather active central nucleus for this object, which of course means that there is another supermassive black hole sitting in the center, quite hungry.
Yeah. So before I gave out my hint, most of the audience agreed with me that they thought it was elliptical. And
Right.
after we gave our hints, now everyone thinks it's a barred spiral galaxy. So can you tell us the answer, Devika?
Fantastic. So I'm going to be using the help of this high resolution image to kind of, put all doubts to rest. So this is an image taken using the 2.2 meter telescope at ESO. And what you see is that you can kind of, in this image, imagine the spiral arms that would be if you're looking at the galaxy like how my hand is sitting in at the moment. So you can see that there are pinkish regions with these dark dust lanes, and that's a lot of star forming activity going on there. And of course, it has a brightish center. You can't see it very clearly, but you can kind of tell that, there's chances or evidence that there are these spiral arms. And that's kind of, what astrophysics, or rather astronomy, is about. It's a lot about visuals and how something appears to you in the sky. And in this particular case, the orientation of an object is so important. There's a lot you can study from edge-on objects, because you can sort of talk about how wide the disk is, for example. You can study the structure of a disk in a spiral galaxy. But in this particular case, the spiral arms are not as evident because of the orientation. So my answer to this would be that, yes, it is essentially a spiral galaxy. I'm not so sure about the bar. I think it's more of a spiral than a barred spiral. I think if it was a bar, you'd probably see a very, maybe that's the thing with shapes, right? You can have varying degrees of it. It's not 0 and 1. So even between spirals and barred spirals, there's a whole range. So you can have a bar that's not as prominent. But yes, in all, it is sort of a spiral galaxy. So well done, everyone who got that.
Yes, well done, everyone. So we've talked about elliptical galaxies. We've seen some spiral galaxies. Are there any other galaxies?
You mean in terms of shapes?
Yeah.
Yeah, so there is, and I like to tell the story because I think, whenever we talk about astronomy and the advancements we make, it's just important to recognize all the effort that our, previous astronomers before us, the generations of astronomers before us have made. And of course, one name that no one can forget is Edwin Hubble, right? So Edwin Hubble, in about 1921, he was one of the first astronomers to classify galaxies based on their shapes, and we call this morphological classification of galaxies. Now, he came up with this arrangement of galaxies that were divided into 4 classes. One was the ellipticals, the other was the spirals, and then he also had a barred spiral, and then he had a 4th category that was called irregulars. So think of them as kind of misfits. They don't fit in any box, and they just kind of get, pushed into the irregular box. So I would say, in this image here, we've just compiled together a high resolution image. What this image shows here is just the 3 broad types. You have elliptical, spirals, and then you have irregulars. So yeah, but going back to Hubble, I'd just like to say that he came up with this classification of galaxies using a 100-inch telescope, which back then in the 1920s was one of the largest telescopes available. And it was called the Hooker telescope. And that was the one he used. And it's quite amazing that even with small telescopes, you can do a lot of very, breakthrough science, because that was what revealed to us that galaxies can have different shapes in terms of the formation and interaction between galaxies and so on. So I would say there is in this case 3, but in general, a 4th type outside of elliptical spirals and barred spirals, which is the irregular galaxies. Yeah.
Fun. So I know of some famous irregular galaxies, and that's the Large Magellanic Cloud or the LMC or the SMC, which is the Small Magellanic Cloud. So can we have a look at an irregular galaxy?
Yeah, you know what? The Magellanic Clouds are my favorite galaxies. I worked a lot on these objects during my PhD, and I still work a lot in these 2 galaxies. And I think they're, especially if you're in the southern hemisphere, they appear as nice little fuzzy patches in the sky, and that's kind of what I really like about them. When I first saw them, when I came to Australia as a student, I just thought it was a cloud. I couldn't believe that it was a galaxy. And I think the name is very befitting because it's called Large Magellanic Cloud and a Small Magellanic Cloud. It's called a cloud, but it's actually a galaxy. But yeah, you can go to say that it is essentially an irregular galaxy. But you know what? The one I've lined up for us today, and how about we kind of go and have a look at it. And this is called the Bernard's Galaxy. And it sits in the Sagittarius constellation. So we'll kind of pull up Stellarium again and go straight into where the center of our galaxy lies. And this is in the Sagittarius constellation. And you can see that there it is, the beautiful Bernard's Galaxy. Now, it's quite close to us relative to all the other ones we've been looking at today. This is just around 2 million light years away, and I say 2 million light years like it's very close, but relative to the other galaxies we've seen today, it is relatively close. And I think, with all these spectacular spiral arms and all these beautiful structures, spiral galaxies get a lot of attention, but I think that irregulars are, just as beautiful, and they have a lot going on as well. And we'll see whether we can have a look at one of the irregular galaxies. That's this one, the Bernards, through our telescope in the observatory. So let's see if Adam or Ben can show us a live view of Bernard's Galaxy. Now, Bernard's Galaxy, remember, it's quite small. So relative to a lot of the other galaxies we've seen today, it's about 7,000 light years across. So for those of you who have seen the Small Magellanic Cloud, it's about the same size as the Small Magellanic Cloud. So it's quite a compact, small-ish kind of galaxy. And it's filled with a lot of blue stars, as you can sort of tell from this Stellarium map. But remember, it is very faint, so I can understand that when you slew the telescope to Bernard's and you're kind of, exposing your telescope to the object, it's going to take a while before you actually are able to come up with the object. Now, here's an example of what happens when you look at a very, very, very faint object through one of our telescopes. And you can see that, we haven't yet been able to capture enough light from Bernard's, and this is because our telescope, once again, is small, but it needs a lot more exposures to be able to garner light. Now, whilst Adam is sort of, bringing up the image of Bernard's galaxies, one of the things I'd like to tell you about Bernard's Galaxy is that it's an interesting question as to how do irregular galaxies form. When it comes to ellipticals, we thought that, ellipticals are basically formed when you have 2 spiral galaxies that merge together. They can form ellipticals. So ideally, when a galaxy forms, it's possible that these are formed as ellipticals, and then they merge, and then they get into being a elliptical galaxy. But in the case of irregulars, I think once again, we think that the shape of this galaxy is possibly because of encounters. So once again, we're going back to the concept of, mergers or encounters between galaxies. So galactic cannibalism and galactic interaction. I'm not sure that's COVID safe, but it still happens in space, and that interacts a lot, and that kind of changes the shape. It changes the properties of the galaxy, the host galaxy, and the galaxy that is interacting with it. So I think that's quite interesting when you think of galaxies in space.
Sorry, Devika. It ties into an audience question that we got a little bit earlier. So okay. Brandon asked, we always see evidence of star formation in galaxies, but do we have evidence of galaxies forming now?
Well, essentially, it's that's an interesting question. So I think it's hard to really say, because ideally what happens is, like I said before, when you have star forming regions in space, we can of course detect them through various frequencies, and it takes a while for these clumps to come together and form a galaxy, and we're talking about millions of years. So it's kind of hard to see a snapshot of these clumps coming together and forming this massive galaxy. We can model these things. So if you take dense star forming regions, you might be able to say, how long would this star forming region here take to build a galaxy of one particular size? So currently it is a little bit difficult, I would think, to view a galaxy forming in action, especially in our time scales, because these things take a long time to be able to come together.
I would also like to say now is a bit of a relative term, because we might see it now, but in reality the galaxy is quite far away, so it could be we're not really seeing it now.
That is a very good point, Gabby. I mean, everything we're observing in the universe is sort of in the past, because galaxies, even if a galaxy is 1.6 million light years away, it takes time for the light to come to us. So the light would have left the galaxy a long time ago, and then it's reaching us now. So what we are studying is not the present time of that galaxy, it's the time it takes for light to travel between the distance of the galaxy and us. And that could be many, many millions of years. So exactly, that's a really, really great point that you brought up. And that's also how, that's also one of the reasons why there is a need to study the oldest galaxies in our universe. We're trying to use telescopes to be able to probe as further away as we can, because it takes a long time for the light from the youngest or the first galaxies to come to us. And we need really good telescopes to be able to capture that and then understand what happened when we had the origin of our universe, essentially, or rather a few 100 million years later. Okay, so I think Adam's got for us an image of the Bernard's galaxy. Now, compared to all the others, you might find this a little unimpressive, guys, but remember that it is a very faint galaxy, and you can sort of start to see this clump put together, and that essentially is the shape of an irregular galaxy. There is really no shape to it. It's essentially just a bit of a clump of stars and gas and dust, and this is kind of the shape it takes. But of course, it is a very interesting galaxy, especially when you study it using telescopes that are a slightly more higher resolution. But of course, here you can tell that there's, you can see the dusty patches, and you can also see bluer, brighter stars that are the youngest stars that sit in this galaxy. Now you'll be surprised, and maybe we can look at a high resolution image of Bernard's galaxy, and what we'll see is you'll be surprised to see that there are star forming regions in Bernard's galaxy as well that show up better in a high resolution image. So what you're looking at here is actually a composite image made with one of the wide field imager cameras on the ESO 2.2 meter telescope. and also data collected from the Atacama Large Millimeter and Submillimeter Array, which is a radio telescope. So there's optical data and radio data that's kind of combined together, and then you can kind of see the real structure of this beautiful irregular galaxy. Now, I want you to remember what you saw before using one of our telescopes. You basically saw the fuzzy patch, but now with a slightly more bigger telescope, well, much bigger telescope, yeah, like that one. So now that you've seen a high resolution image, I hope your eyes are able to kind of detect the image, or rather the on-sky view. So if you have a small but powerful telescope and you have really dark skies, you will be able to observe burnets. Now, one of the details that come out in the ALMA, from the ALMA, that is the radio observations, is that you can see, and these are marked in these small contours, these little green boxes, is these pink dusty gas clouds of dust and gas. Now, this is essentially hydrogen. This is a lot of hydrogen, and this is proxy or representing star-forming regions. So what we're looking at is clouds of cool, dense molecular hydrogen gas. And this is essentially when this gas becomes cool enough, it collapses under its own gravity, and then results in the formation of stars. Now, you'll be surprised if I told you that there's also other molecules in this gas clouds. You, for example, have carbon monoxide. I know it's very dangerous for us, but it works in space. So that's also something that can be detected from the ALMA observations for this star. Now, you know, when you have optical, you can get elements like hydrogen, sulfur, oxygen, and we also saw this in our first episode. But when you go to radio wavelengths, you're also able to pick up and detect molecules, like we just saw molecular hydrogen and also carbon monoxide and other molecules. And these really point to stellar nurseries that sit in this irregular galaxy. So, yeah.
Very interesting. So, I sort of want to hurry up because the next object is one of my favorite objects, and I'm really excited to have a look at this one. So do we want to move on?
Absolutely. Actually, it is also an object. It's a system of objects that I really like, and I think our viewers are going to be blown away by this, because every time I look at it, I'm pretty blown away. So what we're going to do is we're going to kind of step outside our supercluster now. We're going to go really, really far away, guys. So I told you in the start that the Milky Way sits in the Virgo supercluster. So think of it as your local government or your council or your district. And now we're going to go into another district. We're kind of going to go into what we call as the Pavo Indus supercluster, which sits around 200 million light years away. So we're going pretty far away now to look at this amazing system of galaxies I've lined up for you. Now, Adam's revealed to you the system I have for you. This is spectacular display of a galactic triplet. So these are 3 galaxies. Of course, there's more than 3 galaxies in the background. There's stars and stuff, but the obvious ones are these 3 systems, and this is what we're going to look at. Now, they don't really have a fancy name when you come to the galaxies itself. They're basically called with phone numbers of the order of NGC 6769, 6770 and 6771. So that's the galactic triplet system that I thought I'd take you to. So now think of it as you going about 200 million light years away from the planet Earth, okay? Now this is the Stellarium view. So you basically want to look for it in the constellation of Pavo, Indus, and Telescopium. And that's where you're going to find these galactic triplets that sit together. And this is a system, and you'll see in a minute once we gather the on-sky image. Now, this is a system of interacting galaxies. Now, they look pretty close, but in a sense, they're quite far away from each other. They look on sky like as if they're just going to merge in short time, but that's not quite the case. They are still far away, but they will interact in a couple of millions of years. based on the distances they are from each other. Now, the galaxy, okay, the image that Adam is showing us now is basically from the 9.25. So Ben's operating the 9.25. So this is an image taken, it's an on-sky view from our 9.25-inch telescope. And you can kind of see these three galaxies that we saw in Stellarium. And if you have a telescope as big as ours, you're going to just be able to see this spectacular interacting galactic triplet from your backyard, essentially. Now, the upper right one is the 6769, and then to the left is 6770, and then at the bottom is the one that is the 6771. You'll see that the two ones on top, they're quite similar. They're about like spiral galaxies, and we will zoom into them, or we might use one of our other telescopes to look at it, but you can already kind of have a look at the structure. So this is from Stellarium, and you can see that you can see the spiral arms for both the galaxies on top. Both the galaxies possess very bright galactic bulges. Now this is the nucleus of every spiral galaxy, and you can see that it generally has a more reddish kind of a hue, which comes from the color camera, but also the fact that this galactic duo, the ones on top, they have a lot of older stars, and also the one at the bottom as well. Now, one interesting thing about these two galaxies on top is that they are spiral galaxies, and if we zoom into the 9.25-inch view on the sky, as our telescope is getting more and more exposures, you'll see that whilst they are spiral galaxies, the spiral arms look a little bit different. Now, one of them has a very tightly wound spiral arms, and in the other one, you can see the arms look something like this. I look funny as a spiral galaxy with two arms, but you can kind of see the one to my left has this, you know, very characteristic two spiral arms. And that again goes to show that, you know, spiral galaxies come in different flavors. Some of them can have really tightly wound arms and some of them not. If we have a high resolution image of this interacting galactic system like this one here, you'll see some interesting features. And I love looking at this because you can almost see like as if in the two galaxies on top, there are these dark dust lanes that go through them. It looks like someone's just decided to erase off some part of the image. Now, what that is actually dust lanes in the galaxy. And we think that this is because of the fact that these two galaxies might have interacted sometime in the past. Now, when two galaxies kind of interact and, you know, brush against each other, there's a possibility that, you know, material is transferred, of course, and the dust lanes that you see is essentially pointing towards very strong interaction. We also think that the galaxy at the bottom, which is 6771, is also likely to have interacted with this system, because you can see that 6771 has leaking tails, like as if there is a bridge going upwards towards the two galaxies on top. Now, the funny thing with the two galaxies on top is they're really about to interact or have interacted in the past, because you can see like a common envelope around these two galaxies, this dusty common envelope. And that is because they have interacted in the past and are very likely to interact again. Now, this image, this high resolution image, is taken also using one of the ESO telescopes. It is a composite image showing basically the blue, red, and also the ultraviolet channels. So you combine a bunch of broadband images and you put them together, and this is kind of what you get. So ideally, ESO likes to call this the devil's mask, because it looks a bit like, you know, a face and then a bit of a nose. Another name for this system is called the Galactic Tango, because it looks like the two stars that are kind of dancing together. Now, I have a question for Gabby and all our viewers. If you were to name this amazing object, what would you name it? Or this amazing system? of course, you can't call it Devil's Mask or Galactic Tangle because that is taken, but leave it in our comment section and we will follow up with this in the next episode. And we've also been thinking that, because we've had such an amazing audience for episode 1 and for this one, we're sort of going to have some prizes for our favorite answers and maybe even the possibility to make a special appearance on our show. So tell us what you would name this particular object, and you never know, you might be talking with us the next session, or at least saying hello to all our viewers.
I would call it the Galactic Grumpy Old Man, because it sort of looks like a grumpy face.
It does. Okay. So that's Gabby's name. I'm sure you've, I'm not sure what the old men or the grumpy old men think about it, but anyway, that's your name. All right. Right.
So we might have to hurry it up a little bit because we don't want to keep Adam too late, but these two galaxies are coming together, they're merging, but I've also heard of another galaxy that might be merging with us, if you want to elaborate, Devika.
Yeah, so I mean, all of us, well, many of us know that the closest galaxy to our Milky Way, our home galaxy, is the Andromeda galaxy. Andromeda is coming towards us, and we know this because, like I explained before, when you measure the light from a galaxy or a star, what you essentially measure is different atoms that show up in one particular frequency. But in the case of Andromeda, the light that is coming towards us is shifted towards the blue. So we kind of know that Andromeda is moving towards us, and we think that it has like a velocity of about, I don't know, maybe about 100 kilometers per second. So it's coming towards us in that kind of a speed. And based on the distance of Andromeda and also galactic models, we can say that in about 4 to 5 million, or rather billion years, but 4 to 5 billion years, Andromeda is likely to merge with our galaxy. Now, what is going to be the outcome or the end result of Andromeda merging into our Milky Way galaxy is a little bit, I would say, unknown at this stage. Essentially, two spirals, when they merge, they do form ellipticals. That's what our theoretical models tell us. But of course, it might just be that the two galaxies graze. And there's a lot of theoretical models predicting what this merger is going to result in. But of course, we don't have much to worry because, like I said, this is going to be 4 to 5 billion years later, and we don't have much to worry about.
So it's pretty common for galaxies to merge, but when they merge, what's happening to the stars?
Good question, Gabby. So I want you to think of space as when you have galaxies, because of the population or the density of galaxies in space and the size of galaxies in space, you can almost say that in a dense, crowded field, galaxies kind of knock elbows. But the stars inside these galaxies are so far apart that when the galaxies merge, it's not like the two stars are going to wham into each other. That's not going to happen because stars are far away enough to kind of avoid this collision. But galaxies, on the other hand, they're quite massive. And if you look at the distribution of galaxies in the universe, when they do, there's a chance that they are likely to merge with each other or interact with each other. But the stars, because they're so far apart within the galaxy, so distance from one star to another star can be quite far away, or rather far away enough where they don't necessarily collide, if that makes sense. Yeah.
So galaxies are merging, but the universe is expanding.
Yes.
What's all of that?
I've had this conversation on airplanes, on, when I'm trying to wait for my coffee. So that is a very good question. And let me just rephrase it again for our viewers. So we all know from, talks and general understanding that our universe is expanding. So if two galaxies are, say, 1 megaparsec away from each other, then they are going to be expanding from each other based on what we call as the Hubble's constant, which is between 67 and 70 kilometers per second. So what this means is that the universe in itself is expanding and galaxies are receding from each other. But then I've been telling you all along, starting from M83 to this one, that galaxies are going to merge and interact. So how does that happen? Well, essentially what we're seeing here is the battle between expansion and gravitational attraction. So the answer is essentially both win. In larger scales, the universe is expanding and galaxies are going to go away from each other. But in microscopic or smaller scales, the galaxies that are close to each other and can exert gravitational attraction on each other, these galaxies will land up merging. So on smaller scales, gravity wins and it pulls galaxies together. But on larger scales, essentially, expansion wins and it's going to take galaxies away from each other. So it is a very interesting and abstract concept to think about, but yeah.
We just have a quick question. What should we call the new combination galaxy of Milky Way and Andromeda?
Is that a question for me?
Yeah.
Wow, I think, what would I call it? I'd probably call it, how about something to do with, I don't know, actually. I might just...
I would do like Milky Meta.
Yeah, I like that. Or the Andro Way or something.
Yeah, Andro Way.
You know, either of them works. But yes, we have a lot of time to think about it. But yeah, I wonder what the other viewers think. So what would you call the merger between Milky Way and Andromeda? I think I'd call it the Andro Way because that sounds a bit funky.
Yeah.
Anyway.
Well, Devika, this has been amazing. Would we have any more time to look at any more objects?
Well, Gabby, on a normal night, I would say yes, but I do know that you have to attend my lectures tomorrow, and there's a lot of prep material for you.
Yes, so, I do have to do my homework.
Yes, you do. So that I would say maybe not. But you know what? I think, how about, so maybe we kind of leave with a teaser for the next episode.
Well, sounds like a good idea.
Cool. So we're going to be back in about 6 to 8 weeks. And for the next episode, my team and I were thinking we should take advantage of the planetary positions in our night sky. In fact, if you're in the Southern Hemisphere, July, August, well, more so August and September are perfect months to observe and study planets and their moons, and also our own moon, which is spectacular. So I'm planning to bring a very special guest along for the episode who's going to tell us all things planets. And here's a small teaser of what we will see next episode. Now, Saturn is everyone's favorite. So here you have the 9.25-inch telescope looking at Saturn. And you can see the planet in the center and these beautiful rings of Saturn. Now, I'm not going to kind of tell you much about it now, but I will say that in the next episode, we will talk about planets, planetary atmospheres, and also, as you know, just like planet Earth has a moon, other planets also have moons, and these have been observed, and we can observe them using our telescopes. And if you guys have powerful binoculars, then it's something that we can do. So join us in about 6 to 8 weeks for all things planets.
Well, thanks for that, Devika. So we've got a few last minute questions. So for you, can you recommend any books for astronomy enthusiasts?
Yes, I can. I think there is heaps of them. So what we will do is we will add them to our post, so just so that it's going to be recorded. We did this last episode as well. I will say that one of my most favorite textbooks for astronomy, it's more a bedtime book than a textbook, but it's got the information you need. It's called The Universe by Franz Schuh. I remember reading it, and I still read it when I can't sleep. So I think that is a book I would say definitely have a look at. But you know what? My team and I are going to put together a list of books, and we will put that on our website and also as a post for the benefit of all the interested people.
Sounds good. And this might be more of a question for Adam, but Rod asked, why is it an alt-azimuth mount chosen for the Macquarie telescope rather than an equatorial mount?
That's a very interesting answer, but I will let Adam take it because it's going to be fun to hear what he has to say.
Very interesting, Adam.
I just want to make a note that Adam is not the dumbbell nebula as he appears on screen. He's an actual person. But in the spirit of the Olympics, I think the dumbbell nebula, which is Adam's image, is a perfect setting. And yeah, space is into sports as well, guys. So.
All right, thanks so much for that, Devika. So that's the end of our live stream, unfortunately, but we'll be back soon, 6 to 8 weeks. I'd like to say thank you to everyone on the team and also Devika for taking us on this journey. And I'd just like to remind everyone that this episode will be available on Facebook if you want an encore, or if you'd like to share it with your friends later or watch it if you'd like.
Yeah, so thank you, Gabby, and I hope all of you had a great time. As I said in the start, it is a little bit of a different episode even for us because we had to sort of prepare everything online. But, you know, I think we are going to keep doing this, and hopefully we're going to be back in the observatory very soon. But in the meantime, do follow us in the Astronomy Association page, Facebook page, and also the Twitter handle #MQ Space Travels. We are going to put out some fun activities, and like I said, we might have some of you interact with us during our next episode. Now, I'd also like to take this moment to thank my wonderful team. These episodes take a lot of dedication and effort, and this would not be possible without the spectacular team I have. And this time it's rather special because first, the weather gods were in our favor and we had spectacularly clear skies and we could actually look at these objects through our telescopes. And the second is that, Gabby, I got to do this with you, and you're a super keen and stellar student. So it's been a lot of fun, and thank you for joining me on this amazing journey. Yeah.
Thanks, Devika. Does that mean I don't have to do my homework tomorrow?
Unfortunately, it does not mean that. I will see you in class.
All right. Thanks, Devika.
Thank you, everyone. And thanks to the team and all our viewers as well. Bye.
Bye.